Every day, Matt wakes up at 7 a.m., prepares his breakfast, and enjoys a cold glass of water. But what Matt doesn't know is that today and every day, he will consume up to 142 microplastics, many of which will come from this very glass of water. That adds up to 52,000 a year. Over time, this can lead to serious health effects like altered metabolism, neurotoxicity, and increased risk of cancer. Microplastic particles are everywhere and can be fragments of larger plastic products like takeout containers, while some are originally manufactured to be small. While they can be up to 5 millimeters, most are microscopic, and so they go undetected on a daily basis. Current methods of microplastic particle detection are time-consuming and require specialized laboratory training and equipment that costs hundreds of thousands of dollars. So while this guy's been panicking about microplastics, we've developed a solution which will make microplastic particle detection fast, cheap, and achievable for researchers and homeowners alike.
This is us, Team WaterSafe, a group of passionate engineers dedicated to pursuing safe water supplies across the globe.
Here's how the WaterSafe device works. Begin by placing a filter on the filter support. This is a polycarbonate membrane filter. Next, fill the receptacle with drinking water and turn on the pump to force it through the filter. Repeat until you have filtered 1 liter of water. Then, remove the filter, sandwich it between the holder and the mask, and click the holder into its magnetic mount on the translation stage. Next, click the appropriate optical filter into its magnetic mount. Here, we're using a green excitation, so we're using the red 590 nanometer long-pass filter. At this point, you'll be instructed to maximize the quality of the image by adjusting the camera's focus, gain, and exposure time while observing a live feed of the image. Next, you'll take a series of 6 photos of the filter, adjusting the precise position of the filter between each one using the micrometers on the translation stage. When all images are acquired, they're then compiled and analyzed as one composite image, and the results are displayed on the screen.
First and most important, our device shall be able to identify the presence, the concentration, and the size distribution of microplastic particles in water samples. Concerning specific numbers, it translates into our device being able to identify microplastic particles as small as 10 micron at concentrations between 1 to 1,000 particles per liter and with 95% accuracy. One of the most important aspects of our project is that it is a tool for the general public to pursue safer water choices. We therefore set forth requirements that ensure that our device is as intuitive and user-friendly as possible. For the form factor of our device, we wanted it to resemble a tabletop personal computing device.
So one crucial aspect of our project was making a low-cost device. So that means that certain design styles such as spectroscopy or flow cytometry were already off the table because they're way too expensive and complex. So we chose a fluorescence microscope design, but we also chose to remove the dichroic mirror and tube lens that were traditionally used in this style of setup. That way, we're able to reduce costs by a lot and create a device that is more attainable to the user. So we picked a fluorescence microscopy style design, and we did this by choosing a camera and a microscope objective. From these specifications, we were able to achieve a field of view or effective image area of 6.57 by 4.38 millimeters. The goal of our system was to image a filter that was 13 millimeters in diameter. Now this is an issue because our field of view is too small. So the only way to get around this was by creating a mosaic image of our filter. This means taking 6 total images of our filter and then piecing it together. So based on this, we chose to use an XY translation stage that had micron level adjustments. This means that we can precisely locate where our filter is and reconstruct it in post. We are illuminating through an LED ring, and we specifically chose wavelengths of green and blue for our excitation. This light then hits our sample and then experiences fluorescence from the sample itself, and this propagates back up through our fluorescence filters into the microscope objective and lastly into the camera where we detect it. our two specific filters are able to cut out the light that we are exciting with. So that means we only get the fluorescence spectrum. So we designed our system to be very interchangeable and that we can change out which wavelengths we are exciting at and which fluorescence spectrum we are using.
So the software subsystem needed to accomplish our sponsor's two main requests: that we count the plastics and that we size the plastics. This is where we take the image taken by the camera subsystem and apply what we call thresholding to it. This is how we determine the boundary between what is a particle and what isn't a particle. We find areas of relatively high intensity. Once we find these areas of high intensity, we apply Owatsu thresholding. This thresholding is available in an open source library called scikit-image, and it basically maximizes the variance between what we classify as a particle and what we don't classify as a particle. Once we've determined these boundaries, we can apply particle counting software to go ahead and count our particles. To accomplish goal number 2, we take these regions identified and calculate what's called the ferrite's diameter. From there, we can show an image of the identified particles and a size distribution.
For MVP1, we chose to use an existing fluorescence microscope that cost over $20,000, and we tested our handmade microplastics on it, and we imaged them successfully. Now, today, we have a setup that does the same thing for less than $2,500. And we did this using a much simpler setup and lower cost components. In addition, we can also achieve 10 micron resolution.
With this minimum viable product, we were able to accurately differentiate one microplastic from its background, do the same thing with multiple microplastics, experiment with different thresholding techniques, and we were able to determine that we would have a hard time differentiating our contaminants in our water from our microplastics.
To test the accuracy of our device, we imaged 6 samples with varying concentrations of microplastics. In each image, we hand-counted the number of particles present to get a value for concentration and used a micron-scale ruler to measure the size of a range of particles. We then ran these images through analysis with our algorithm and compared the results. Ultimately, our device passed its acceptance test, performing with 95% accuracy. Despite our ability to detect and size particles, our device as of now is unable to distinguish between microplastics and other contaminants, including dust. While comparing the fluorescence of particles at different wavelengths holds potential to mitigate this, more data is needed to make a proper assessment. We believe, however, that our project provides a solid foundation for future iterations to improve upon.
Together, we can engineer a new future of low-cost particle detection. While this may conclude our project, for us, it is just the beginning.